Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about verification and validation of simulation-based network performance evaluation. In previous sessions, we've seen that there are three main ways of doing network performance evaluation: experimentation, analytical modeling, and simulation modeling. Simulation modeling is a kind of a hybrid technique in which we are working on a model of the real system, but we are also doing experimentation on this model of the real system. And therefore, there are many things in which we can go wrong. The first thing that we can go wrong in is in creating the right model. So the step of ensuring that we have the right model to work with is known as validation. Thereafter, when we have a right model for the purpose of our study, we have to transform it to a computer program or a computational model. We can also go wrong in this step, and ensuring that we do not go wrong in this step is known as verification. Finally, when we have a computer program that is a valid representation of the real system for the purpose of our study, we have to do experiments on this, and then we have to statistically analyze the output, because any finite number of observations will not give us the exact parameter of the model. And again, when we analyze statistically the output, we are only analyzing the model. Furthermore, the model is also just an approximation of the real system. So to have any credibility in the results that we have from simulation-based modeling, it is essential that we take verification, validation, and statistical analysis of output very seriously. We can visualize this entire cycle as shown on the slide. So we start from the system and we make a conceptual model of the system, in which we make various kinds of approximations and we abstract away all details that are extraneous to the purpose of our study, and only include those details that are relevant for the purpose of our study. And then we have a conceptual model. This creation of the conceptual model is an iterative process, and we have to continuously calibrate this model according to the real system. Thereafter, we have to ensure that we create a verified computerized model that is free from all bugs and is doing the thing that we want it to do exactly. In other words, verification is building the model correctly, while validation was building the correct model. And thereafter, another step involving validation is that once we have a computerized model, we can run experiments on this and gather observations. So the real test of any model is that it has some predictive ability. So the output that we would be getting from our computer program should be close to the output we would have achieved if it was possible and efficient to do this experimentation on the real system. So this is, in a nutshell, a discussion of verification and validation. Now I can tell you the outline of today's session. So initially, I'm going to talk about some common mistakes in simulation, and they include mistakes in validation, mistakes in verification, as well as mistakes in proper statistical analysis of the simulation output. Thereafter, I would be talking about concrete steps and techniques that we can use to do verification and validation. And finally, I'm going to talk about how to ensure credibility of our simulations, because the purpose of doing simulations is to gain insight and to enable decision makers to make good judgments. But for them to believe your simulation results, it is important that your simulation results are credible or they are believable. So we'd be talking about steps that we can take to ensure that our results are credible. We start with the discussion of common mistakes in simulations. So the first mistake that we can make is that we can include inappropriate amount of detail. So in analytical modeling, we are forced to only look at the most important aspects of the system, because if we include too many details or if we make the system too realistic, it becomes typically very complex. So complex that we cannot analyze it in a tractable and efficient fashion. But in simulation, there is no such limitation. You can throw in as much detail as you want. But obviously, having too much detail is not good, because the purpose of creating the model in the first place is to have a simpler substitute for the real system in which we only have the essential items, and all the complexities that are not relevant to the purpose of our study have been eliminated or have been abstracted away. So one extreme that we can err in is to have too much details in our system. So if there are too many details, typically it would involve more cost, more time, more programming time, and also more execution time. So all in all, it is not a good thing to do. We should not be including more detail than we must have. At the other end, we can also err on the side of including too few details. In other words, we have simplified the model so much that now it's not an accurate enough representation of the system. So we would be talking about this further on in this session, but this is a very fine balancing line, and we need to find the right balance. Also, another aspect of common simulation mistakes is to deal with software practices. We may choose a programming language which we are familiar with, but it may not be the best choice for our simulation. So we know that there are various options of programming the computer model of the simulation. We can make use of a general purpose programming language like C, Java, or Python. We can also make use of simulation languages. Languages like Simula, languages like GASP, like GPSS, and there are many other languages. Finally, we can also deal with simulation packages. Packages like NS2, like Omnet, Qualnet, and other such simulation packages. The important thing here is that we choose the simulation language and the simulation package, whichever is appropriate for our task. Because if we go about inventing everything on our own, chances are that we'd be making an error. So if we can find a simulation language which does what we want it to do, so that can actually eliminate a lot of programming time. Secondly, if we are using a verified program, chances are that it will not be buggy. But if we create the same thing ourselves, chances are more that we would create a bug. Therefore, it's important that we find the platform and the language which is most appropriate for our simulation study. The third thing we can go wrong in representing randomness, because in computer systems, we are often making use of deterministic methods of creating random numbers. We've covered this in a previous session. We called such generation methods pseudo-random number generation methods. So when we are doing that, it is important that we just do not blindly trust whatever option we have in our simulation program or in our package. We have to know at the minimum if it has some basic good properties. So it is advisable to use a well-known random number generator, because it is very easy to make errors in this regard. So one should be careful in choosing the right random number generator. Secondly, when we are concerning ourselves with random number generators for creating random numbers, we know that such methods are deterministic. So they typically have a starting seed which initializes this algorithm. And if we give the same seed to the algorithm, we're going to get the same output. So the thing is that we have to ensure that the seeds are properly chosen. So if we have multiple sources of randomness in our simulation, as an example, we have a router on which packets are arriving and they are being serviced, we need randomness sources for representing the arrival process as well as the service process. So if we are to make use of pseudo-random number generation methods, we must ensure that the random numbers generated are independent. So we have to make sure that we are not making use of the same seeds for the different streams that we need. So we need one stream for the arrival process, another stream for the service process. We must not be using the same seeds, and if our algorithm is such that it cannot work with 0 value as the seed number, we must ensure that we do not give 0 as the seed. Typically, it is an important thing that we do not use a random number generation method that is too picky about seeds, because it is a source of errors, and typically people unintentionally make these mistakes. So we must choose a good random number generating method and also choose the right seed for that method. And also the various streams must have independence. We don't want correlation amongst the random numbers, because that can lead to invalid conclusions from the simulation study. Finally, we can also err in making wrong statistical analysis of the output. For example, we run a simulation and we get 50 observations, and we take the mean of it, and then we can just present the average, and if perchance our algorithm is better than the competition or the literature, that's it, we can say that our output is better. Typically, this is a common mistake and a very wrong thing to do scientifically, because the output of simulation is a random variable. In other words, if we do the simulation again, the output we will be having would be different. If we do it again, it will again be different. So how are we then to deal with such output? We can only deal with it statistically, and therefore we must provide proper confidence intervals. We cannot just rely on a single number to represent the random variable. We need to either specify the distribution, or we can specify a confidence interval that, okay, this is our point estimator of the central value, but we also have a bound of interval where we expect this mean to be. So this is important. We should consider the output of simulation as a random variable, and we must therefore properly statistically analyze the output. And these things would be covered in a dedicated session on proper statistical analysis of output. So I'm just currently very briefly describing the things that we should be careful about. We should also be careful in not doing too short a simulation, because if we're doing a very short simulation, chances are that we will not reach the steady state. Also, the starting point of a simulation is typically important for a transient simulation, because if we are only going to run the simulation for a short while, then the position in which we start the simulation typically has a large effect on the output that you're going to get. So we must take care of these things so as to ensure that our output or our analysis is not biased, or it's not totally invalid. Okay, we can also now talk about a checklist for simulation that we must always do before we have results that we believe in. So we've done a simulation, but we must ensure that we follow the guidelines of this checklist before doing the simulation, during the simulation, and after the simulation. So the steps we must ensure before the simulation are, first of all, we have to ensure that the goal of the simulation is properly specified, because even the model is dependent on the goal of the simulation. For the same system, we can have many different models, and the model that is right depends on the goal of your simulation. For certain simulations, we can abstract away most details, but in certain simulations, especially if we want to make absolute judgments between different alternatives, it is important that we have a very realistic system. So the specification of the goals should be the first thing that we do, and this would be covered in the conceptual model. We should have the goal explicitly stated there. Secondly, after having defined the goal, it's important that the model be created according to that. So the level of details that we incorporate should be commensurate with our goal, as just mentioned. Further on, typically creating a simulator is a team exercise, especially if you're going to do this for a company as a practitioner. In such cases, we need to have many different skills. We need to have skills of modeling the system. We need to have skills of converting the model into a computer program. So we need software engineering skills. We also need statistical skills in analyzing the output of simulations. So we must have a balanced team in which all the necessary skills are present, because creating a simulation is, if done well, it's a difficult thing, but too often it's not done well, and therefore we have the problem of too many simulation results that do not count for anything, and that has led to a credibility crisis. So we would see later on in this session that many people now are very skeptical about simulation results. So we must ensure that we do proper simulations so that our results are credible, and all the effort that goes in towards this regard is useful for solving our problem. Lastly, we must dedicate enough time for this simulation, or we should be adjusting our goals according to the time we have. Typically, creating a software is a long-term commitment. You need months. Typically, you will not be able to complete a simulation and design it and properly analyze it in matters of days. Typically, you require months, and it becomes, as the scale of the project becomes larger and larger, the complexity of creating a valid simulation is also increases. So we must ensure that we do not give too short a time for a simulation in which the goals are very ambitious. So if we are careful right at the start, then chances are that we will not get into trouble later on. So these were all the things that we had to do before even doing the first run with the simulation. Now, when we are developing the simulation program, the earlier things were relevant even before programming the computer simulation. But now, during development of the computerized model, we can think about many issues. The first issue that we must think about is the random number generator that we are using. Is it a valid random number generator, especially in the context of being uniform and independent? So when we talked of random number generation, we talked of various tests that we can perform. And in your textbook, you can find many guidelines. So before we actually start programming the computer model, we need to ensure that we have a good source of random number generation. And we must become familiar with the demands of that random number generator. Secondly, during the development phase, especially if this is a large project and not an individual project, it must be ensured that all the stakeholders are aware of the developments. Because if we isolate the programmers from the other people, then chances are that they would be creating an outdated model. So we have to ensure, because the system is dynamic, typically whatever we want to capture changes, the network traffic changes, the algorithms, various parts of the system are going to change. And therefore, we need to have an up-to-date expectations of what we want to model. And therefore, there must be continuous communication between the various entities, the various stakeholders that are part of the simulation project. And lastly, something that is very important but often overlooked. We must have documentation of the system. Typically, when students are working on simulation projects, they tend to think that their work is insignificant or is very easy to understand. But even if they were to themselves revisit the simulation after a few months, chances are that they will not completely understand the thoughts that went behind the design of the simulation. So it's important for the purpose of revisiting the simulation and for the purpose of eliminating extra time in trying to discover how the simulation was done, that we have a good documentation system right at the beginning of the project, and we do this continuously. So as a good software engineering practice, even in the code itself, we must have self-documenting comments in which we are specifying how different pieces of codes are going to work. And lastly, in the checklist regarding simulations, we can talk about the various guidelines that apply to the output of the simulation. So once we have the simulation running, there are various things that we can do. We can properly do output analysis, and for that we have to ensure that the simulation length is appropriate. Secondly, we have to see that the initial transients are removed before computing of the results, because as mentioned before, the starting conditions of simulations have an effect on the results, especially if this is a steady state simulation. So in such cases, we must remove the initial transients, because that is not typical of the steady state statistic of whatever we're trying to estimate. Thirdly, and this is very typical in simulation studies, the output is autocorrelated. In other words, the successive observations that we have are dependent on each other. Typically, similar observations would follow, and therefore we have a correlation amongst the different observations that we make. So we cannot straight away apply the typical statistical methods that we have that assume IID random variables. If you recall, IID random variables are independent and identically distributed. So the keyword there is independent. But simulation output for most part is dependent. And this is what you should be assuming, and you should assume otherwise only when you can show that the simulation output is indeed independent. So assuming that the output is dependent, then we have to take steps to ensure that we do proper statistical analysis of the output. So we have a dedicated session on output analysis in which we'll be covering these issues. Finally, in regards to output analysis, all simulation output is random in nature. So if we were to do the experiment again, you would have a different output. So we cannot simply give definitive answers from just a single simulation. From a single simulation, we can only create an estimate, and therefore it's important that we express our results by a confidence interval. And then there are steps in validation and verification, things that we shall be covering in the later part of today's session. Things like, has the model been verified thoroughly? Has the model been validated before using its results? If there are any surprising results, we must ensure that we have at least some idea of why such results are coming. We have to be careful in this regard, because we cannot completely predict everything that is going to happen in a simulation. But if something is clearly wrong, then we must very carefully understand what's the reason of such mysterious results, because it is very possible that such mysterious results are resulting from an error in programming the computer simulation model, or it is due to some obvious mistake in the conceptual model itself. And lastly, also as it concerns to verification, we need to see if the simulation language or the simulation program, whatever random number generator it is using, we must know what that random number generator is, and we must know the properties of that generator. We can only depend on simulations if we are confident that the random numbers that we are assuming are in fact random. Okay, now another important thing that I would like to emphasize is that simulations is just not a concern of creating models. It is a concern of using models to understand the system and develop insights. So we need to understand from which entities errors can arise. So we've seen that to have a proper simulation result that is credible, we need to first of all validate the model as well as do proper statistical analysis. Let's see now the interrelationship between these two things. So to understand that, let us assume that we are trying to estimate the true parameter of our population which concerns with the real system. Let's call that mu s. Imagine that we are trying to estimate the true mean of the real system, some parameter. So in a simulation model, we are not working with the real system. We are working with a substitute of the real system which we are calling a model. So when we are working with a computer model, we are then we have transformed the model into a computer program. So there are two kinds of errors that can happen. The first kind of error is that the model that you have, it's not an accurate enough representation of the real system. Let's call the true parameter of your model as mu m. So the point I'm trying to make is that mu m is not the same as mu s typically. If your model is an approximation, then there would be some difference between mu m and mu s. If your model is a good enough representation of the system, then this difference between mu s and mu m would be small. If it is very large, then our model is not good enough. So this is the first source of errors that we can have. The second source of error is that we cannot completely estimate the real mean of the model too, because we are not analytically analyzing this model. We are analyzing it through simulations. So when we run simulations again and again, typically we can only form an estimate of the true mean of the model. And therefore, there is estimation involved here as well. So first of all, we are approximating from the real system, we are approximating. And then we are estimating from that approximation. So there are two kinds of errors that can happen. And the overall error is the sum of these two errors. To ensure that the first error does not arise, we have to do proper validation. To ensure that the second error does not arise, we have to do proper statistical analysis of the output. So by these two techniques, we can minimize the overall error, and therefore, in a nutshell, we can say that validation of simulation results is not just an exercise in model making, but it requires model validation as well as sound output analysis. Let us now talk about various verification and validation techniques. Let's start by talking about verification. In verification, we are concerning ourselves with the question that is the conceptual model, assumptions about the system structure, components, parameters, values, abstractions, etc., accurately translated into a simulation model. So essentially, we are talking of the transformation of the conceptual model into a computational model that is typically a software program. In other words, we have to ensure that proper software engineering techniques are followed in this transformation. So let's just summarize few techniques that we can use. I can summarize all the techniques by just 4 or 5 words, and then we can provide more detail on these guidelines. The first thing is we should start simple. The second thing is we should modularize. The third thing is we should continuously debug. The fourth thing is animate wherever possible. And fifthly, document. Everything you do, you should properly document it. So I now offer an explanation on these very brief guidelines by talking firstly about software engineering good practices. So the first thing is we should not go about creating the entire program in one go. We should have a top-down modular design in which, first of all, the first thing that we want to do is to decide on the structure of the overall program, to modularize the system so as to break down the overall complexity into manageable proportions. And once we have these modules, we can start by assuming very simple modules. So instead of having a very elaborate module, we can, for example, just hard code whatever output we are expecting from this module and see if the other modules that are dependent on this module are working fine with it. And from this, creating a top-down modular design, we can iteratively plug in more details, make the modules more and more realistic as per the goal of our study, and move towards the goal in this iterative fashion. So an important thing is we should start simple. We should not try to do everything in one go, because then when you have a very large program, it is very hard to diagnose where exactly the problem is. And then as a general practice, we should have the method of introducing sanity checks in our code. So for example, we can ensure that we are printing various statistics that are relevant to the simulation, so that whenever we run the simulation, we get an estimate of how the simulation is working. Also, there are many things that we know must be true. For example, if you have a probabilistic model, the sum of the probabilities of all the events must add up to 1. If you have a system in which you have job flow balance, then the number of arrivals must be equal to the number of departures. So in every system, we have such conditions that we know that they must be true. So you can always ensure a check if these things are actually met or not. Also, it is very important, and I emphasize this is very important but often overlooked, that you have a proper documentation system. Even if you're working on an individual project, please make sure that you properly document your code, because you never know when you might have to revisit this code, and also you don't know if this code is going to be used by other people. A very good practice that I encourage, and that is encouraged by most experts in the field of network simulation, is to make your code available for external investigation and replication. So if you have created an algorithm and you have checked it using network simulation tools, whatever scripts you have, you must make them available so that other people can replicate your findings. Only if you allow other people to replicate your findings would your results be really credible. Otherwise, people are just accepting your words on faith, because we know a bedrock of scientific principle is the idea of replication. We do not believe just on the claims of someone, but we must have the methods of replicating the same result ourselves. So to ensure that other people are able to do that, you must document your code. Also, it is important that we have a proper version control system, because especially when many people are working on the same project, chances are that there would be many different versions of the same computer program. And therefore, to avoid problems that may arise from such a scenario, it is very wise that we have a proper version control system, especially if you would like to commit back to an earlier version of the program which was working well. Also, when a person is developing a computer simulation program, he enters into a mental rut in which he is envisioning everything according to his own interpretation, which is a good thing, except that if some errors are being made, then that person is not the best person to judge that. So if we can have independent evaluation, then it really helps in picking out mistakes and errors. So if you are working on a project and you have a group of people, it would be wise to have different people working on developing the simulation program and other people who are independently evaluating the program. So if we have two different points of view, chances are that they would have a more complete picture of how things are moving. Another thing that is very important is the ability to trace how things work in a sample run of a simulation. So to exploit this, we can make use of traces. And most simulation languages and packages offer the ability to trace how the sample went. So for example, it would list down the various events that happened, and at the same time also the state of the various state variables of the simulation. It is also very wise if we can develop methods of visualizing the state of the information by devising appropriate operational graphics or methods of animation in which we can see how different entities are moving around the simulation and what are the states of various state variables. Using this, we can develop intuition of how the real system works, and we can understand the dynamics of that system. Another method that we can use for ensuring verification or for ensuring that the computational model is a valid transformation of the conceptual model is to ensure face validity. In other words, we ask subject matter experts to see if everything is working out fine. So we can see if the input to output transformation is plausible. So if something is clearly wrong, a subject matter expert is likely to spot that error. And therefore, we can quickly spot some errors just by exposing our model to a subject matter expert. And the subject matter expert can play around with the system and see what different outputs are coming for different inputs. And from that, we can see if there are some errors. We note here that this method can also be used for validation of the conceptual model. So another thing that we can use is to ensure consistency checks. So we have a conceptual model that is valid, but to ensure that it is correctly being transformed into a computer program, we can make use of the practice of doing proper consistency checks, in which we may think of a degeneracy test, in which we give extreme input values to the system and see how the system behaves to that. And in many cases, we know how the system should behave to such extreme values. So for example, if we are considering a queuing system, then if the arrival rate is more than the service rate, then the system is unstable and the queue size would keep on growing. So we can see if that thing is actually met in the simulation of a queuing system. And we can also see if randomness is being modeled correctly or not. The first step here is to actually see what algorithm is being used, and then we must ensure that we are ensuring seed independence and also that the streams of random numbers are independent from each other. A very important step that we can take in this regard, which can actually reduce the errors that we can have in the verification phase, is to choose the right simulation language. Because as mentioned earlier, simulation languages are developed by experts and they already have many features that are common to all simulations. So instead of doing everything yourself, you may actually choose a simulation language that has already implemented most of the things that you want to do, and then you can focus on the things that are specific to your own study. For example, event scheduler is there in every simulation language, in every discrete event simulation language. So if you can make use of that, you do not have to program that yourself in your own simulator. So whenever we have the choice, we should seriously consider the various options we have. So from now onwards, we would be talking about validation of conceptual models and seeing how we can ensure that our model is a valid enough representation of the system. So in validation, we are really concerning ourselves with the question, does the conceptual model, assumptions about system structure, components, parameters, values, abstractions, etc., accurately capture the relevant properties of the real system that are important for this simulation study? So I keep on emphasizing importance for your simulation study because it is important to understand that there is no completely accurate, completely valid model. Models are by definition approximations. If we wanted a completely accurate model, we could have worked with the real system instead. The purpose of having a model is to have a simplified approximation which we can analyze more efficiently. If there is no such model and if you want to capture all the details, then you can actually experiment with the real system. So the first thing is that all models are approximations, and we don't seek an absolutely valid model because an absolutely valid model would be too complex for any practical utility. We also note that model credibility is actually a function of the details that we put in, but also at the cost of putting in too much detail, we have the question associated risk of increasing the cost of the system. If we put in too much detail, typically that would require more time, more programming time, more execution time, and this translates into higher cost of the model. So we need to find the sweet spot in which we are getting the best value for our effort. And the real dilemma then for a modeler is to find the 10% of the system that accounts for 90% of the behavior that you are interested in. So this is a difficult thing, and this is more of an art than a science. So there is no mechanical way of creating a model. Every modeler would create a model that may be different from the models of other people. There are many, many different ways of looking at the same real system. So we need to find the model, the approximation that works best for us. In this regard, we can see the guidelines offered by Alan Pritzker, who was the creator of the simulation language GASP and also many other languages. And he was really a pioneer in the usage of discrete event simulations. So we should value his guidelines. And from all his experience, he came up with some guidelines. The important thing is that creating a model does not only require software engineering skills or just statistical skills or just skills about the system. You need to have a balance of all these skills. And Alan Pritzker says that conceptualizing a model requires system knowledge, engineering judgments, and model building tools. Secondly, something that is very important and that I would have time to come to again is that the secret of being a good modeler is the ability to remodel. So the reason for that is offered in the third advice, which is that the modeling process is evolutionary because the act of modeling reveals information, important information, piecemeal in a manner that is one at a time. And because of that, when you have more information, you know more about the system. And then you can remodel your system. You can calibrate it to improve it. Fourth guideline offered by Pritzker is that the problem statement is the primary controlling element in model-based problem solving, something that we've already talked about. We've said that the most important thing in a simulation-based study is defining the goal of that study, because everything that follows directly from the goal. The fifth guideline is that a model should be evaluated according to its usefulness. From an absolute perspective, a model is neither good or bad, nor is it neutral. In other words, if the model is working for you, if it is helping you make good judgments, then it is a good model. Otherwise, it's not a good model, regardless of how many people worked on it, who worked on it, because the criteria of judging the goodness of a model is that does it help you solve problems? Is it useful for you? And this thing is encapsulated by the final guideline that we'll be talking about. The purpose of simulation modeling is knowledge and understanding, not models. So we are not creating a model just for the sake of it. We're creating a model because we want to understand the real system. If it helps us understand the real system, then it is a good model. Otherwise, it is not useful for us. Now, we can talk about the stages of calibrating the system by looking at the graphic you can see on the slide now. The real system is a complex system that we want to understand. And to make it more manageable, we make a simplified model of it. So this is represented as the initial model. We compare the model to reality. We try to validate this model, and from that we can make some decisions on how to improve this model. So remember Alan Pritzker's guideline about remodeling. The key to being a good modeler is the ability to remodel. Once you've discovered something new, you can go back and calibrate the system and improve it. So we do that here by revising the model, and we have a first revision of the original model. We again compare it to reality, and from that we get new information, and from that we can calibrate the system again to have a new revision of the model that is better than the earlier revisions. And this is the way modeling works iteratively. So, and this will keep on going. So, having now mentioned the benefits of remodeling and of calibrating the system, I can now offer you some basic principles of V&V, verification and validation, that we must follow and keep in our mind. The first thing is that verification and validation is not a one-off thing. It's not something to be done at the end of the project. It's something that has to be done and taken care of throughout the project. Secondly, validation and verification is not a binary variable in which you have a valid model or you do not have a valid model. The idea here is that this thing is relative, and it is relative to your goal. The third thing, we've talked about this before, we want to prevent the developer's bias, and therefore we want independent evaluation. The fourth thing is V&V is relative. So as mentioned before, our goals dictate what model we should be creating, and the model that we have is to be judged relative to our goals. So the fifth principle is that we must explicitly plan and document how we are going to validate and verify our system. And lastly, even if you have a validated and verified system, people are not going to believe you unless your simulation model is credible. So credibility is something else from verification and validation. You need to do verification and validation to come to credibility. But to achieve credibility, you may have to do some additional things. For example, you might have to open up your code for external replication. We'll be covering more about credibility later on in this session. To summarize this portion on validation, let me again summarize the main things we've covered. So, to validate simulation results, we need to validate not only the simulation model, but also the output. So, let me summarize the entire process, the things that we can do in 5 steps. So, the first step is that you build a model that has high face validity, and to ensure that, you must incorporate or get feedback from subject matter experts. The second thing that you can do is to validate the conceptual model assumptions. And the third thing is to validate the input model and the workload model. We'll be having a specific session on input modeling, which is going to talk about how we can capture the various sources of randomness from the environment that interacts with the system, and we have to model it so that we can drive the simulation. The fourth thing that we should care about is that we can validate the system by checking the input to output transformation of the model and by comparing it to the corresponding system's input-output transformation. For this, we can make use of historical data as well as resort to experiments on a real system, but we must ensure that the data set that we use from the historical data should not be the one from which the model was created, because in that case, the model would fit that data set, essentially because that is where the model was created. This must be a data set that is new to the model, and we see how the model predicts the output, and we see its correspondence to the real system. If there is good correspondence, then we have a valid system. And finally, we have to validate the simulation results by performing a proper statistical analysis of simulation output. Okay, now we can talk very briefly about credibility of simulations. Why is there a credibility problem with network simulations and what we can do about it? So the first thing is, I'm going to tell you some quotes about network simulations that networking experts have given. There is growing skepticism about the role of simulation in network performance evaluation study. This is not to discourage you from using simulations, but to put before you the problems that simulation studies can have and which we must avoid. So the first quote is from an influential paper from Polikowski in 2002, who said that some claim that stochastic simulation as a performance evaluation tool is misused, and that the spread of this phenomena is so wide that one can speak about a deep credibility crisis. Further on, there are other important people who have written about the problem of the credibility of simulation results. For example, Sally Floyd and Vern Paxson, in their influential paper written in 2001, titled "Why We Don't Know How to Simulate the Internet," said that network simulators make it easier for researchers to create simulations, but the researchers themselves remain responsible for making their use of simulation relevant and insightful, rather than irrelevant or misleading. They go on to say that rigorous arguments from inappropriate assumptions lead to durable nonsense. In other words, you must have appropriate assumptions, and on the basis of that only can you form valid conclusions using rigorous arguments. Because if we couple rigorous arguments with inappropriate assumptions, we get nonsense out, and that nonsense is durable because people believe that thing is very rigorous. So to ensure that we do not fall into this trap, we have to ensure a repeatability of our results. In this regard, there are some social issues as well as technical issues. The social issues are that one must be ready to share their code with the public so that they may replicate the findings on their own. And also we need to give scholarly credit on such replications of experiments. The technical issues are that we need to specify everything that we use to validate our setting and our statistical analysis, explicitly state that in our papers. So only by expressing these things explicitly would our results and our simulation become credible. So now I would be summarizing the entire lecture, and I'd be telling the important things we discussed. The most important thing we discussed was that in a simulation-based network performance evaluation study, verification and validation is an essential step. It's not something that is to be taken lightly. We must explicitly state everything we did to verify and validate our models. In other words, it's not enough that we have used some standard simulation language program or we've used some standard model. We need to define whatever steps we've taken to find a correspondence between our model and reality, and also how we have verified that our model is bug-free. We should not be limiting verification and validation to just the end of the project. It should be planned and it should be incorporated throughout the project, and we should be continuously remodeling a system, our models, so that we have always the best model that captures the system in terms of details that are commensurate with our goals. So that ends today's session. I'll see you next time, inshallah. Assalamu alaikum.